the cloud. Should be recording, should be making sound. All right, hopefully everything's right. So today I'm going to be talking about programmable logic, like what's actually inside of your FPGAs, for example. Before I do that, I would like to point out a potential issue that some of you will have with your lab 2, when you're doing the echo back, is for a lot of people, it will echo back one successfully, like one character, and the second one will screw up. And when you do it one at a time, it seems fine, but it may not necessarily actually work that way. So there is a program called Termite that if I had my FPGA here and we're connected, I can actually send entire strings, sentences, one after another, which then will echo back. I kind of recommend using Termite to run a test on your system if you have time. It doesn't have to work this way for lab 2, but it will have to work that way for future labs. So it's just kind of future-proofing your design if you end up needing that, or if you end up having time to do that. Okay. So programmable logic, right? This is really nice because hopefully everyone did something in 2700 where you didn't have to, hand design huge blocks of logic, right? We're using an HDL, in our case, VHDL. Now, this is kind of incredibly important because we're designing these massive digital systems. Even lab 1 and 2 probably have thousands of components linked into them, right? Building that by hand would be an absolute nightmare. We will actually show you some ways that people do build state machines by hand. Not really anymore. It would be kind of tedious, but it is possible. And then we'll kind of go through the different types of programmable logic that exist or have existed in recent history. So there are 2 main types that we'll look at that are going to be, one is logic that can be programmed one time and logic that can be reprogrammed many times, right? Your FPGA that you have currently falls into the latter category. So here's kind of your programmable logic hierarchy, where you're going to either have factory programmable or field programmable devices. Now, factory programmable are these ROM and MPGA types. These are going to have some specific type of process that is used to tell which gates to connect. All of them will have that process, but in the case of factory programmable, it's going to be with a tool that you don't have access to. So for example, they may have like ultraviolet light used to go in and fuse some gates together in order to program it. In order to do that, you would have to peel back apart the chip and get a machine that could highly accurately go through with 180 nanometer or 14 nanometer resolution and tell each of these to fuse. Not exactly within the realm of something that we could do. Field programmable devices, on the other hand, are divided into these 3 categories generally. And really the difference is just their level of complexity, right? SPLD is simple programmable logic device. CPLD is a complex programmable logic device. And the FPGA is really just a super complicated programmable logic device. We'll go over the architecture of these throughout this lab. But you can see that they've broken down the SPLDs into further ones. This SPLD category is not super common anymore just because CPLDs are incredibly cheap now. So why use a few gates when you can use many gates for a penny is pretty much what it ends up coming down to. Let's see. I'll get to this in a second. We'll go over kind of specific cases of these, but if we look at the PLA and the PAL in particular, these ones are around still a little bit anyways, and you can really have CPLDs that you would call a PLA or PAL. And these are, if you've seen the diagrams where there's wires that come in from the top and then wires that go out from the side into gates, right? That's where this diagram coming from, is the PLA and the PAL. And the PAL is just a special case of the PLA, in that a PLA has a programmable and OR gates, whereas the PAL has fixed OR gates, which I'll show you an example why that kind of matters when we get into it.
Where do PIC chips fall under?
The PICs are generally microprocessors, so they are neither of them. You can implement a PIC on an FPGA pretty easily, actually, but they're microcontrollers. Very simple microcontrollers. Okay, so your CPLD, SPLD, FPGAs look something like this, right? So the simple tends to be low density and a few hundred gates. CPLD is medium density and 5 to 12,000-ish gates, right? And you can see that why, like, a few hundred gates could be 500. This crossover already exists anyways, that borderline. Just use a CPLD. This book is old, you may have noticed, so a lot of these are going to be out of date. The theory still kind of stands. The architectures have evolved a little bit, and the companies are still around. So Lattice, Cypress, Xilinx, Altera, I have one of each of those FPGAs sitting in my office right now that have been made within the last couple of years. The difference is Xilinx no longer uses Spartans. Really, that was the old crap that if you had taken this 2 years ago, you had been using, and you'd have a nightmare because they don't even support the software to program those Spartans anymore. They still sell them, they just don't support them. It's kind of funny.
Are those the ones Woodison used?
Yes. Yeah. I tend to use Xilinx, Lattice, and Altera. All three I've had experience with. They all have kind of trade-offs. We use Xilinx here because most of the companies locally use Xilinx. Combined Xilinx and Altera has actually been recently purchased by Intel. Xilinx and Altera combined account for something like 80% of the FPGA market with just those two. Lattice has like 8% market share of the remaining. Cypress has like another 3%, and the remaining 12% is scattered over another dozen companies that I've never touched, but they're around. Each kind of specialize in their own way. Xilinx tends to be very user-friendly. It's very easy to use. Altera has some incredibly powerful IP cores compared to Xilinx in my experience. They're a little more complicated to use. And Lattice specializes in very low power kind of FPGAs. That's where I've run into them the most, is if I'm trying to use low power FPGAs. But they're all going to make some mixture of those some combination of that, right? Because they want a wide product line. So picking your FPGA when you're looking like an industry often really comes down to, if you really don't need very many things, you jump to an CPLD and you pick Xilinx or Altera. You're crazy if you use anything else, pretty much. If you're using an FPGA, you're usually end up not picking between brands. You're usually picking whatever your company uses now. Just because it's really nice to have code that already works, right? It's somewhat difficult to switch between brands because of IP cores, which you probably don't all know what that means yet, but we'll get there. Yeah.
So for, say, a company uses a PLC to control their machine movements and things.
Yeah.
What would you use an FPGA in industry to do? Like, would you replace a PLC with an FPGA? Or is that just too big of a scope for it?
No, so you could absolutely replace a PLC with an FPGA. In fact, a lot of modern high-tech manufacturing machines are already doing that. Part of the reason that PLCs are still popular is because they are so simple to program, right? They're used ladder logic instead of HDLs, which is fairly trivial to learn. It takes once you've graduated and you have all of the experience under your belt of being through undergrad, it might take you a week to teach yourself ladder logic at most.
You say ladder logic, does that mean just sequentially?
Yes, ladder logic it looks like a series of ladders that the signal comes from the top, goes through down to the ground, right? And then you build branches that come off and kind of build a cascade of rungs that talk to each other and slowly just pass through the information. But if you were to go and open up, so I have some background in print, like large scale print, okay? And if you went and looked at a 20-year-old printing press that was, say, I mean, some of them are as long as this room. They would have a bunch of PLC modules that you would switch out, you could program and fine tune. If you were to go open up a 5-year-old one, especially cutting edge ones, they have an FPGA in them because they're getting more and more advanced and the PLC capabilities are unable to keep up with the requirements of print. One of the cool examples is right now, there's a company that makes a huge press that's designed to put through hundreds of thousands of sheets of paper each hour. It is about as long as this room, is actually a little bit longer. And it has these 12-foot cooling towers so that they can shrink the length of it so that the paper shoots through, gets printed on, shoots up so the ink can dry, like, right, because you layer down each color separately. So it shoots up so the ink, that first ink can dry, shoots back down and goes through the next color. Now, what they found in a problem is that when they shoot the ink onto the paper, right, so they just shoot a little droplet onto the ink to make a dot. The issue is that when it hits there, it splatters. Or it hits there, makes a bubble, and then streaks. So what they end up doing is shooting it at an angle so that the ink actually starts with a forward-leaning bubble, and then the air pressure, the air friction actually pushes it back into a droplet, right? Doing that on a PLC is remarkably difficult. Doing that kind of timing on an FPGA, however, is not that hard once you understand the physics of it. So yeah, PLCs exist. Many of you will run into them, but they are very older technology with some severe limitations. Okay, so one way we can implement logic, for example, in a programmable logic is read-only memories, or ROM. ROMs can be either one-time program or reprogrammable. A lot of the reprogrammable ROMs, however, need UV light to erase them. So they're not really field reprogrammable. They take a lot of space as well because they don't do a lot of thinking. They're really just lookup tables. So the way a ROM works is they have an input, which is the address. So ABC is an address. If I give that address, the 3 input of 0, 1, 0, then the outputs F0 to 3 would come in here, look at the 0, 1, 0, and output 0, 1, 1, 1. Okay, so the left side is the address, the right side is the actual contents of the ROM. Okay, so they're going to have some amount of access logic that says if this number is put in, put out this vector. You guys will be using ROM in one of your later projects to store some files into in order to run signals through. Is
that kind of like a MUX?
It is not like a MUX. The logic that controls the output is a MUX, however. So the input literally goes into the input of a MUX. So this select is selecting a MUX channel, which then is directed to the output. Yeah. So in general, if you generalize this, you're going to have an N by M ROM, where you're going to have n in 2 to the n words, right? That just tells you how many rows there are. So if you have 4 bits, you 2 to the 4 rows. And then you need how many bits in each output word. So word is the thing that we use for the vector that's the output. So you have an input word, output word. The number of rows is determined by the length of the input word. Okay. If asked what the size of this is, right, in this case, this is an 8x4 ROM. Even though it has like 16, it has 8 rows. So it's the number of rows by the number of bits in the output word. Okay. You can implement just about any logic in a ROM. So in this case, it's sequential, okay? So a ROM by itself is sequential logic, not combinational. So it has memory, the ROM has memory, but it's still sequential logic. The reason is, if I put in a combination of bits, it just spews out an output number of bits. So let's look at an adder, which we use all the time because they're really nice and simple. If I have a 2-bit adder, I want to add X to Y. What I do is I use the bits of X and the bits of Y as the address, and it just goes out and looks up the result, right? This is just a truth table for a 4-bit adder. And all it's doing is saying, well, I know all possible combinations, the addition, that's the truth table. What is the output? So for example, if we come in and say 0, 1 plus 1, 1, the output is 1, 0, 0, right? That's just, we did some addition. We did it in a ROM. Is it in the homework? I haven't looked at it yet, but yes.
Where you make a table of all the number of bits.
Yes, yeah. The homework 6, I think.
The one we just did.
Homework 5 says sign up lookup table.
Oh yeah, yes. A lookup table and ROM. A lookup table would be implemented in a ROM. It doesn't have to be a ROM, right? Because you can also use array. So a lookup table is a ROM is one specific way to implement a lookup table. But yeah, it's the same idea where you're just enumerating all possible answers. And then you draw the block like this and say it's 16 by 3. It's an adder. I put in the inputs, it spews out the outputs. Done. It is not, however, resource friendly, right? Compared to an adder, this is a lot of logic because I need a mux in order to select it, which is already at least, if you're talking 2 input AND gates, this is probably at least 6 of them for just the mux, which is already more logic than the adder is. No, it actually has longer gate delays because it is very easy to implement in programmable logic. This was like the first way that you would do programmable logic is you would just make a ROM because it was very easy to do. It didn't require a lot of dynamic changes. So let's go ahead, do a quick example problem and ask the question, compute the size of a ROM required to implement an 8-to-3 priority encoder. Now, what a priority encoder is it takes in 8 inputs and outputs a 3-bit code. So that code, and we'll just ignore D for right now, don't worry. The D is just saying if there is one or not, right? Anyways, all it's saying is what is the position of the most significant bit? Okay, so that's why there's all these don't cares. There are 8 bits in the input. So there should be 2 to the 8. However, if there is a 1 at Y4, I don't care what Y0 to Y3 is. That's what this truth table is saying. I know you probably haven't seen a truth table with don't cares on the left side, but it's just saying that this combination for all, so the 1, 0, 0, 0 here in any other combination is going to have the same output. So just copy and paste these rows a bunch of times and change the don't cares to other things, which would be horrible to draw. Anyways, So the question is, how big is the ROM required in order for me to make this? How many rows should there be? So here we have 8. We have 1 row for each bit. 3, 4, 5, 6, 7, 8, 9. Oh yeah, plus the zeros. 9 rows.
You have a lot of don't cares in them.
Yes. So what do those don't cares mean for the implementation of the ROM though? A lot of empty space, basically. We end up with actually 2 to the 8th rows. So we are 2 to the 8 or 256 by 3.
You're only using 9 of those.
But we only really care about 9 of those. But there's no way to simplify ROM logic. So 8 inputs for, there's a bunch of text. You can go look up this problem. It's in the book. But the main takeaway is it has 8 inputs, 4 outputs. So it needs 2 to the 8th by 4. You could really get away with 2 to the 8th by 3 because there's with some really simple logic, right? You don't really need this output, but they're assuming that you don't have any other logic to access. And so you need just a flag that says if you have an encoding success. Let's go ahead and build a state machine out of ROM. And so let's go ahead and build ROM out of, sorry, a state machine out of ROM. So we're going to have this truth table for the ROM. How do we do this? Okay, so we're going to build just BCD to XS3 code converter that was done like back in chapter 1. You don't really need to know what it's doing in order to read a state table, right? So if we look at the state table, if we're in state 0 and X is 0, we go to state 1. If X is 1, we go to state 2, right? We know how to read state tables. This is the table that we want to implement in a ROM. Really not that hard. So remember our initial state machines where they have input logic, right? That to decode the input to calculate the next state. So we'd call that the next state logic. And then you have an output decoder to the output or to decode the output. Well, here by this state table, we have one output Z. That's going to be an output of the ROM. The next state is also just an output of the ROM. And I just need 1 bit in the ROM for each output and 1 bit for each required next state bit. So here I can look up, I see that I have 7 states, right? A 6, a 0 index, I have 7 states. That means I'm going to have 1 excess state because I need 2 to the 3 bits. Or 2 to 3 states, so 3 bits. So here are those 3 bits, right? So D0 is my output Z. D1 to 3 are my next state. The next state gets calculated on Q1 plus Q2 plus Q3 plus. Then at the rising edge of a clock, this flip-flop takes the input Q3 and stores it on the output Q3 and puts that into the next state input of the ROM, right? So if we start at state 0 here, then we're looking at the input. So I'm here at S0, if X0 or X1. So let's say X1, X is 1. That means we're going to go to state 2. So it's going to have X is 1 here at A0. The ROM is going to look at, okay, currently I'm in 0, 0, 0. So that's my address is 1, 0, 0, 0. My ROM then goes, what is my output? Well, it has all possible variations enumerated. It puts the corresponding S2 state on D1, D2, D3. And Z is, for the case of X equals 1, 0. So it would have a 0 on the D0. Next clock cycle, that updates and we go change state. Basically, here's the truth table that would show what's happening. So here's the state table where if X is 0 right here, and I'm in 0, 0, 0, then the output, which is on the right side, is 0, 0, 1 with an output of 1. Whereas if my x is 1, which is the example I mentioned before, 0, 1, 0 is our next state and our output is 0. This is our ROM. So this, the left side of the column, will be your lookup. That's not stored in the ROM, that's just an input to a mux pretty much. And the right side is the contents of the ROM that will be spewed out if that particular address is given.
So you obviously then have to go in and put all that information into the ROM first.
Yes. Yep. Yeah. And so ROM is typically, in the earliest versions, was only factory programmable. So at the factory, they would make the state machine and they would send it out. And if they wanted to change it, they would have to literally swap out a chip. And this would be made with discrete components. So this would be literally one chip is the ROM, and then you'd have 3 different flip-flop chips. Eventually, they would make state machine chips that would have a little bit of programmability in them that you could tinker with what the next state is, and they would have built-in flip-flops, and then you just have to provide the clock, and it would provide the inputs and outputs, but still they weren't very programmable. But this is early technology. It's not completely unused now, but it is kind of dated. Because now we've moved on to things more like the PLA. So the PLA, as I mentioned, is a type of simple programmable logic. And it's going to have some number of inputs that come into an AND array. And then those ANDs get ORed together to put the output. What kind of expression is that? Yes, it's a sum of products expression, right? AND gates into OR gates, sum of products. So more specifically, if we dig in and it looks like this, we'll take this expression, these expressions. So I want F to be the min term 0, 1, 4, and 6, which just so happen to simplify down to these equations, not A, not B, or A, not C, right? Well, let's go look at this. Here, for F0, is this OR gate, right? That's the top level gate, it's the OR. Let's trace it back. Well, it has one expression that is not A, not B. That's this AND gate. So not A and not B. It fuses, this A comes in, goes through an inverter. We fuse a connection at the output of that inverter. That's not A, attached to this AND gate array. We fuse not B into there, it outputs and now I fuse the OR to the outputs of those. Yes?
Did that cause a hazard?
No. Well, I would have to go look at the K-map is the quickest, easy way to do that.
Did you see that A going through an inverter?
Yeah, you may end up with a hazard there. And so then you would go back and you would add an additional term in order to prevent the hazard. The other gates are all implemented exactly the same way, right? And if we go to look at what do these gates look like, we're not actually quite building them like we would have talked about in 2700. We're building them a little bit like this, where they're using pull-up resistors and pull-down transistors. So for example, if A comes in and I get not A here, that means I get A here. So if A is true, this wire, this top horizontal wire, gets pulled to 0, right? Because it turns on that transistor. In contrast, if A is 0 and it's not turned on, this wire gets pulled up to V+. So it's basically what we would call open drain, right? Which you talked about hopefully in 2700. So the pull-up resistor is responsible for pulling it up and the transistor pulls it down. The downside to doing this type of architecture with a pull-up resistor is what? Yeah, actually it is slow because you're relying on the pull-up resistor to pull it up at the speed of the RC network that gets created from the parasitics of all of these transistors. It is not a driven signal, it just gets pulled up. So it's actually quicker because it pulls to 0 and there's 0 resistance, right? Which whatever the on resistance of the transistor is, which is determined just by how wide you make it. So that is really easy to make it fast. Whereas if you're using pull-up resistors, you don't necessarily want them to be small because the smaller they are, the faster they go, but also the more static power consumption they have. Because if it's pulling it up, it's just continually burning power through that, which is a problem, right? So here at the bottom, I've just kind of illuminated, oops, click the button, how like you would build an NMOS NOR gate with this kind of pull-up architecture, which they're equivalent, right? So if either X1 or X2 is turning on this pull down, it goes to 0. If they're both on, it's fine, but you only need one. So there's actually a really simple, really compact logic. It is just not that fast. There is an interesting byproduct that happens from having the PLA architecture like this. So let's go back and look at this really quick. So if I have this not A, not B term, what's really cool is that it gets reused in F0 and F2. So the simplification is not necessarily the minimum output of the K-map, but it is actually the minimum number of expressions. So if you're looking at the K-maps, sorry, the minimum number of implicants across all K-maps. So you have to actually solve all of your K-maps in such a way as to consider what is happening in the other K-maps. So for example, let's look at this one here, which is this big square in the middle. We could use that one, and that would end up with the minimum logic for that specific K-map. However, if you look at the other K-maps, the left circle is used over in F2 and the right circle is used over in F3, right? The implicants. So rather than creating a third implicant in this F1 expression, you are actually better off using more implicants that are mirrored across the other two, because that will reuse one wire. It'll actually save resources to use a less minimized expression. You get the same thing kind of around here where you might want to circle 8, but not really, right? Because you're creating a whole new group of AND gates that you have to create. And the interesting one is the size of these AND gates are fixed anyways. So it doesn't help you because they're fusing that connection one way or another. That AND gate size exists already. So you're not really simplifying anything by using those bigger implicants. It's just not important in the actual implementation of a PLA. This is a little bit more rigorous version of what I just described, but I don't think we need to go through it. So just some notation. A lot of times we'll see this type of inverter, which is just the same as this circuit, right? There's one path through, there's not. This happens all the time in modern FPGAs where it doesn't really matter what you do with your output. You will always have a and not A generated at the same time. It's just which one do you hook into? So there's some weird tricks with the actual technology that come into what do we care about with simplification. Also in this diagram, right, this is just to illuminate that if I have this type of connection, it means they're connected. Rather than drawing 3 different inputs for my AND gate, I do this, right? So this horizontal wire is actually a bus that can have some number of things connected into it. If they are not fused, what would be the, right? This is a 3-input AND gate. That bus has 3 lines. All 3 lines are always connected to this AND gate. It's just whether or not C gets fused. What happens to that 3rd input if C is not fused to it? What is it connected to instead? What must it be connected to in order for this AND gate to work?
1.
Yes, it must be a 1. So it's whether you're connected to 1 or C, right? The reason it has to be a 1, right, is if it's a 0, then the AND gate can never be true and it just wouldn't work. So you're going to start with something like this, where you're going to have 2 inputs, 1 and 2, that come in, and nothing is fused. Once you program it, it's going to come in. It might be something with like light. It might be a pulse of electricity that it might have actual fuses in there that they are designed to melt, and they send a high voltage across them and they melt together and make that connection. That is obviously programmed 1 and only 1 time. You can't undo that connection, but that is a technology that is used and can be very helpful for things that you don't want people to be able to change. So once it's programmed, we would mark it as having these fuses, right? I1 is both of these lines. It's just hard programmed there. And then the I2s connect here, and we just tell it the AND gate here then is I1 and not I2. And the other row is not I1 and I2. And then they OR those together and you get this expression. Done, right? So if I ask you a question on the exam where I give you a picture of something like this, but without the connections, I may ask you to draw the bubbles and create for me some logic expression in a PLA. Hopefully very easy. People have missed that question way more often than they should though. So, okay. This is just, once again, back to our good old friend, the full adder. This is what a full adder would look like in a PLA, right? Where I've just come down. These are my input signals. The vertical lines are my inputs. The horizontal line are the inputs to the AND gates, their AND gate expression, where I'm fusing, you know, X, not X, not Y, C in. Okay. Fuse that out. Go through all of them. I have sum and C out. Done. I have made myself a full adder. This is, again, not the simplest expression that you can get. It's not the easiest way to do it, but it is a very effective way of implementing it in a programmable logic type technology. Yeah. Yeah. It's just not doing anything, which in the case of an OR gate means all of these are fused to 1, so that the AND gates, but then you have to disconnect the output of this and fuse here to 0. Otherwise, the output is always true, right? The other way is I might go in and fuse them all to 0 so that output is just always off. That's where your synthesis tools come in, is you're not actually going to have to worry about what that gate is doing. The synthesis will make that decision for you. Okay, let me get caught up on my notes so I don't miss things. Terms that is. Okay. Right. Okay. So real quick before I forget, there's 2 different versions of this, right? This is actually a PAL because only the AND gates are programmable. Right. The OR gates are just fixed. They're just connected. I don't have any of those cross fusion connections here. So this is that special case of the PLA, which is called a PAL, where we only program the AND gates. Okay, we can then go ahead and use something like a PAL to make a state machine, for example, or memory or whatever else we want. We would do that again simply by connecting a flip-flop to the output of the decision. Each clock period that outputs Q feeds it back around and can inform the AND gates of what the next output should be. Right? So it's considering what is my current state, inputting that to the ANDs and ORs, it outputs into D, the clock hits, it updates whatever is put onto D to Q and Q bar, that spins back around and updates its decision. Then generally you'll have an output tri-state gate, which is where if the enable is on, it passes through. If it's not enabled, then it disconnects. right? Hopefully you did this in 2700. I know mine did, in order to create IO ports, input and output ports. Okay. We can then move up a scale and talk more about, oh, before I do this, we now have what they call flash erasable PALs or PLAs, meaning that you can reprogram them. They end up calling these PLDs. So then we'll have SPLD, CPLD, right? That kind of thing. PLD is kind of the umbrella term for all of that stuff. Let's see if I even want to talk about this. Yeah, let's go ahead. Oh, I didn't copy it in. Crap. Okay, that's too bad. All right. Well, here we'll look at it a little bit in the case of a term that we want to introduce now is an output macro cell. And what the output macro cell is, again, like I kind of talked about with that output enabled tri-state buffer, is how do we use input and outputs on one pin, right? Because if you think about your FPGA, you're programming it and you're telling it in the port declaration whether it's an input or an output. How does it implement that? Well, it actually is an output macro cell, which is really pretty simple, where the output is driven or not by a tri-state buffer. If I'm not enabled, I can then use it as an input. So then the input comes in here, flows through this wire, and goes into a mux, right? Now, the output of this mux can either take the input, Q bar, and feed it back out and do something with it, or it can take the input, the IO port, and feed it out through here. And all of that is determined by the select signal coming from an output select mux. Okay, so these mux comes from programmable interconnects. So what this is showing you is that you have this big cell that no matter what you're doing, all of this has to exist. This is designed into your PLD. Then all you're doing is fusing various ports so that they can be programmed to be either in a state where it is an input or an output. So if you have a situation where S1 and S0 are equal to each other, and they're 0. So we have 0, 0 on this mux. We take the 0th input, which passes Q straight on through to the output, and Q bar feeds back and is accessible to the system. Okay, which is here. This is my logic expression that is getting implemented, put into the output macro cell, and fed back so that I can reuse this decision, this function, right? So if I need a cascade of functions, this is how it would do it. So it would have one function come in here, get fed back out. This would be programmed into another and or array that would be programmed, and it would come back into another macro cell. So you just sit and feedback these through. Now, if we switch it and so that they're both ones, the path goes the other direction. We have the output of the function. It flows directly into this inverter, which then gets passed through this select channel 3, right? 1, 1 is select channel 3 on the mux. That gets passed to the output. It is also passed back into this mux. There's a 1 here. We can then use what the output is seeing. That you might do with like the clock, right? Because you need an output clock so that other devices can synchronize to it, but you also need access to it internally. That's why if you go and look at your constraints file that are provided for you on the line that says 100 megahertz clock, it's an output. Is because it is connected to a pin, so you may as well be able to use it, but it is also available internally. It does, however, that pin is dedicated for the clock specifically because that path is very optimized so that the clock is easily accessible to all other devices inside of the FPGA. So you might end up something like this. This is an old CPLD from Xilinx that they call their Cool Runner series, where you're going to kind of break it down, where you're going to have IOs that go into these function blocks. Those are like those and or gates, for example. They might be a little more complicated or specialized. And then you have an interconnect array that gets programmed to tell it how these function blocks are connected together and how the IOs are routed between inputs to function block. Okay. This interconnect can have, sorry, let me get to my notes so I don't skip over stuff real quick. Yeah, so one thing I highlighted that I need to make sure I say, so each of these function blocks, you could call individually a PLA. So when I start building up a more complex, a CPLD, it is really a stack of a bunch of PLAs or PALs, depending, that then get connected together into something more complicated. Okay. Yeah, let's go ahead and hit here. This is kind of the simplified version of that, right? So I talked about that function block, the PLA. You have that macro cell that I went over before. You connect into the output of the macro cell, and then it goes into the programmable enable to tell it whether it's an input, output, does it use internally, externally. Then we can go and hook it up to the flip-flops. These macro cells will very often have flip-flops. These flip-flops feed back around, right? So let's go back to that macro cell real quick. See, it has this flip-flop. We can use that flip-flop as the memory part of a state machine, because notice that it has an input coming from an equation, and it has an output that goes back out that can be used for the next state and output decoder logic. So that's all this is showing you, is that we want to build it up, use this and or array, access the flip-flop of that macro cell, feed it back around into your and arrays, and now you have yourself a state machine. It doesn't take anything extra. You just utilize the resources already available in your output macro cells. You can then go a step further and say, let's pretend we go all the way back and we programmed those PLAs to be a adder. We can now have multiple full adders connected together. They're connected to these registers that are really just the flip-flops inside of the macro cell. So now we can store each of the bits of that adder. So that's kind of what a CPLD is doing. In fact, your FPGA is not that different. We can skip this. This is pretty much the same concept, right? Where there's some AND arrays that is the adders, they feed into the OR gates, and then we use the flip-flops inside those macro cells to feed back around, make our decision. It's just a closer view of that same kind of idea. Okay. Make sure I didn't miss anything. Okay, so yeah, we're ready to move on to talking about FPGAs. So the FPGAs, one of the things that is a kind of consequence of them is they tend to be slower than CPLDs. And this is just simply a byproduct of the massive amount of programmability available in the FPGA. So they have huge long interconnects, so you have to worry about how fast can your clock propagate, right? Which if we had a VLSI course, which I don't think we do yet, but we will someday, we would talk about this propagation issue in clocks, where if your FPGA is large and your clock is fast, you could have one cell, two different cells on different sides of the FPGA that are using the same clock. But the clock is so fast that the actual delay of when the clock gets there puts them out of sync. And so when they push that back into the interconnect, they're updating not at the same time, but rather at the propagation delay from the origination of the clock to the cells and then back to whatever the combination cell is. So what if you end up in high speed design of FPGAs in industry, which is one of the better paying, higher demand fields because it is so frustrating, half of your life will be spent trying to deal with clocking issues because it's all about just making sure that the clock routing and timing is functional. Just like with the other one, your big ones, Xilinx and Altera are your big ones. Lattice kind of follows it up. I haven't seen an Actel or Atmel FPGA in years, and I think one of Actel or Atmel is actually still around. I think Atmel is still around, but I think they make mostly microprocessors. Yeah.
How fast is high speed?
Once you break about 400 megahertz is kind of the rule of thumb. It's a little fuzzy on what is high speed, and you can kind of calculate it literally by the size of your FPGA versus the clock speed is pretty much all it comes down to. Kind of like how if you've taken transmission line stuff, if you've been in EM, who here is in EM? Anyone? Okay, you're taking it. Okay, well, I guess you guys don't know that. You'll get there in electromagnetics. That will actually kind of illuminate where this speed limit comes from. Anyways, I'm pretty sure Actel and QuickLogic, I think, are both dead companies now, and Atmel focuses mostly on microcontrollers, if I remember right. I don't really use microcontrollers very often, so I don't know. So your FPGA is going to have some architecture that looks like this, generally. This is super common, where you're going to have a whole bunch of little logic blocks that are all around. You're going to have some interconnect that tells it how each of these connect together. When you program it, it makes mux connections, right? Or fuses them, however it wants to do it. Modern ones tend to be muxes just because we want it to be reprogrammable. And then you have the output logics near the edge. You will also very often, near the edge of your FPGA, have what are called DSP cores. These are very specialized blocks of logic that aren't simply like a PLA or a PAL. They actually have dedicated circuits for optimized like FFTs, for example, that allow it to do very complex operations as fast as possible. So if you go look at the specifications, it will actually tell you not only how many logic blocks it has, but also how many adders, multipliers, FFT blocks, and various other dedicated dedicated logic blocks. This helps make up for the kind of limit of FPGA, because if you can do things in fewer clock cycles, it is effectively faster. So they try and make that easy for you. The types of interconnects that you're going to run into. One thing I want to point out too, in an FPGA, yours is not configured this way, but can be. You can, let me doodle. Have different regions of the FPGA. So for example, you might have it separated like so. And in this block uses a 3 volt, more likely 3.3 volt, but I don't want to draw it. And this is 1.8 volt region, so that you can have different voltages for IOs to different components. So I have 2 seniors that took this class from me last year that are working on an FPGA project for me. They actually have 4 different voltages. They have 1.2, 1.8, 3.3, and 1 volt regions. The reason is they need a 1.8 volt to interface with a memory device. They need 3.3 volts to interface with an analog to digital converter. They need 1.2 volts to interface to a USB 3.0 chip, and their 1 volt is their internal clock voltage. So each of these FPGAs are going to have pins all over that are different power supplies that you will configure and then tell the constraints file what voltage they're supposed to be. So again, if you go look at the constraints file I provided for you, it actually has 3.3 somewhere in that constraints file statement. The reason is because all of your pins are 3.3 volts. If it won't break the machine, the FPGA, most of the time if you give it the wrong voltage. What it does do, however, is it is incapable of properly calculating the propagation delay, making clocking at high speeds very difficult, right? Because it needs to know, am I going from 0 to 1 volt, or am I going 0 to 3.3 volts? One of those obviously takes longer, right? That's why we like low voltages, is it is actually faster to use smaller voltage. However, when you get very low voltages, it starts making the design more and more difficult because you have to start dealing with more non-idealities of the transistors. The lower the voltage, once you go below 1 volt, there are devices like this, but you have to start treating even digital electronics a little bit like analog. And once you're down in that region, you also have to start accounting for things like quantum tunneling of electrons, because you can actually measure the current that you lose at that level. So this is kind of modern design issues. Most of you don't have to worry about it. Most people kind of stick to simpler designs, because FPGAs by nature are fully parallel circuits, right? Or at least massively parallel. So since they can do so many things at the same time, they're very fast compared to any microprocessor. Because a microprocessor has to deal with things like queuing, right? It has to, all right, I'll get to this when I can. FPGAs have no such thing. Okay. The top left, so these are just different versions of interconnect. The top left is very common. I would say as of 6 years ago, which is a long time in digital, this was the dominant type of architecture, where you have each individual logic block there with interconnect that kind of goes all over the place. And then when the synthesizer goes and builds it, it tries to make anything that talks to each other with high speed close to each other in this fabric. Tries to localize it. You can actually, on your FPGA, if you go into Vivado, when you make a design, you can actually go click on the implementation and you can view where all of your logic is implemented. It will actually tell you. It's kind of cool to look at sometimes. The other three are all kind of less common because they require more complex implementations and the adjacency issues become more defined. This hierarchical one is kind of an interesting one. It is used on occasion because of its benefit of you have little local logic interconnects that all act very quickly together. And then you have the global interconnect that is there for slower speed connections. You will oftentimes see this one with like the high speed sections of FPGAs. You will actually see hybrid interconnect versions, because this one, when you put your DSP cores all really close together, is helpful. And then you send the data off in parallel later. Okay, memory. We're going to switch a little bit and let me make sure I didn't miss anything. Some of these questions you may end up like in the homework. I don't remember. You may have to go back and look a little bit, because it's going to talk about EEPROM and EEPROM. There's a little bit difference in their programmability. I'm not going to spend the time in this lecture kind of on that too in depth. Don't be afraid of going and reading the book. Unlike my sensors course, if you're one of the people in there, this book is actually fairly accurate if old. My sensors book is atrocious. Okay, so basically what you're going to do is, if you want to build memory, is it all going to be based on a transistor? No surprise, right? Everything is transistors all the way down. You're going to have some little memory cell that's going to plug into a transistor that has a writing wire that will allow it to pass or not, based on the contents of the memory. You can also like plug those memory cells into a multiplexer and have it go. Those memory cells are going to look something like this. Now, I actually don't really expect you to memorize or really keep this in your head, but I do want you to be familiar with how memory is built. at least a little bit, because there is, I would assume that at least 2 of you will probably end up working for Micron. There we go. Which is a fairly large company here in Utah that makes memory. They make a whole lot of memory. They make other things, but they mostly make memory here. So at least this way you've seen something that's a memory device before. So if you end up with like a co-op interview or something for them, you can go like, oh yeah, I've seen memory. Basically, let's go ahead and look at it where you're going to have not bit and bit, where if you have a 1 here on bit line and you want to put an input in here that turns this on, then the 1 gets pushed in and connected to these cells. Okay. Those then can pull from VDD. Notice that it's connected to this node and that node, which then turns on this transistor. That voltage gets pulled up into here. Not bit is stored on here, and you can then start storing voltage inside of that little memory cell, depending on how you're asserting the not bit and whether you actually want to read from the memory. And then you can also put them onto from here back on the bit lines. They're much more complicated than this now. This is, 20-year-old memory cells. Let me see what I decided to tell you about this one. Oh, I should call it out. These, if you don't recognize the architecture right off the bat, that's okay. It's literally just linked latches. That's why it holds memories. They're literally just latches that latch onto one value or the other based on the assertion signals. This type of memory is volatile. I actually told myself I'm going to skip this one, so that's fine. And this is the main summary page that actually is what you do need to know. So there are these different kinds of programming technologies. I've kind of alluded to these as we've been building there. The first is SRAM. SRAM is volatile. It is reprogrammable, but has massive overhead, medium resistance, and high capacitance. High capacitance is bad because it slows things down, right? High resistance is bad because it slows things down. Area overhead is bad because it makes your FPGA have to be larger, right? However, this is what you guys are currently using on your FPGAs because it's very fast to program and very easy to work with. However, it disappears when you turn the FPGA off. In contrast, you have EEPROM and EEPROM. Where I've worked, everyone just says EEPROM for everything, which gets very confusing, but both are non-volatile. They can be, well, the difference is here out of circuit versus in circuit reprogrammable. EEPROM has the benefit of being very small, whereas in circuit reprogrammability is desirable, right? We don't have to pull it out of the circuit. We don't have to do a bunch of overhead to make it work, but it's bigger. Anti-fuse is this kind of thing that I was talking about that is not reprogrammable. This is where we hit it with the current and it literally just locks together and it's done. But its benefit is it's very fast because it's low capacitance, low resistance, low overhead, because it's one and done. So if you're trying to design a very high speed system, you do this. Downside is once you've programmed it, that's it. And you will find out throughout the course of this lab that that's undesirable because you're going to design your system, you're going to test it thoroughly with a test bench, and you're going to feel super confident that it's going to work, and it won't. So you end up throwing these things away. So when you test it, it doesn't work, you throw it away, right? Kind of sucks. Fortunately, things are getting cheaper and cheaper, but there are still, once you start talking FPGAs, they get expensive real quick. I'm using in the project that I'm working on right now, I'm using, I guess what you would call the high end of the bottom tier, and it's still a $150 FPGA. It is quite easy to go spend $500+ on a modern FPGA. And that's just the chip. I don't even mean the dev board like you guys have. So what you guys have, the dev board is $150 dev board. The FPGA itself that's on that is about $30. $22 in better times, but supply chain issues have been a nightmare and everything costs too much. Actually, right now, I think they cost $100. I think yours have actually recently jumped. The ones that you guys are using, I think just hit $100. Yeah. Yeah, the extra FPGA, I think, hit 100. So I think the boards have gone up to 300. Yeah, it's supply chain is a nightmare right now. This is just another implementation of logic where we're really now just combining ideas that we've talked about before, where you can have lookup table-based programmable logic, right? So we have ROMs essentially, but they're reprogrammable, so they're not really read-only memory. It doesn't need anything fancy like ultraviolet light to shine on them to reset them. You just send electrical impulses. This is your bit stream, right? So you generate the bit stream, you send it over there, it sends electrical impulses, creates lookup tables. We're calling them LUTs, not ROMs, because they are reprogrammable. Those lookup tables then feed an output macro cell, right? And that looks kind of familiar. That's all that really is. It's just simplified. It doesn't have the feedback. That's all it is, right? This FPGA is just building all of these SPLD, CPLD, PLA into little segments that get stitched together, and boom, we have a reprogrammable FPGA. So for example, this one, if we want to take some function of A, B, and C, it goes, looks it up, it puts the output on, and then we can make it clocked or not clocked. We simply do that because it is generating both the unclocked to this mux and the clocked to this mux, and then the mux select tells it, is it clocked or not clocked? Now, you'll notice the downside to this is this mux and this flip-flop always exist. It's just whether or not you're using them. This knowledge that this exists can be very helpful to you as you debug, because you will sometimes get errors that say weird things like you cannot assign a clocked signal to an unclocked node. That is basically telling you that you've done something funky here, where you're trying to clock and not clock it at the same time. So go back, look at your code, see if you're doing something weird. I don't think I'm going to have you do this semester. Let me know if I accidentally do. I will change the homework. I want you to know it exists. There is a whole design methodology for designing logic strictly based off of muxes. You can implement any function just off of logic or just off of muxes. I'm not going to do that to you this semester. So if I end up in the homework, let me know, and just don't do it, because I don't think it's going to be a good use of our time. Last semester when I taught this, I was already crunched for time and teaching all the things that I wanted and getting you through the project. So I'm lightening the load a little bit, which I think you can all be appreciative of. So that's all that's talking about. This is out of order. I really wish I had noticed that before, because this is really kind of useful. All this is showing is that interconnect that we talked about before. This is a demonstration of how it works, right? Where this logic block gets connected into this wire. It sends it over to a switching matrix that tells it whether it should make a transition into a different column or passes it through and connects it to another logic block. It will again try to make sure that it is all as close as possible as it can be. Here we go. I think I only got like a minute left, so I was just making sure I get to the thing that I actually care about here at the end. So this is a programmable IO block for an FPGA. This is actually based on a Xilinx FPGA, so it's pretty close, but this is again like what, a decade old or something, more than, it's like 13 years old. So FPGAs are changing all the time to get better. What this is showing is, all right, let me settle in here real quick. You can have I'll just start from the top down, right? So you have this 3-state output enable that goes in and programs whether or not we want the output buffer enabled. Is it an output, right? This is the same idea of the macro cell. I believe the homework 6 ends up having you actually program a macro cell just to kind of get it in your head because this idea is important. You can have the output signal that comes through and is applied to this mux. The mux selects either clocked or not clocked. In this case, it's selecting not clocked. The output buffer allows it to pass through and it goes out to the IO pad. In the case of your FPGA, the IO pad is actually a little ball of metal that sits on the bottom of the device and is soldered onto that. The flip-flop has the enable signal. You can also feed back and have the input signals to go to other logic blocks, right? They're all very similar. All the devices are similar. It's just slowly increasing the level of complexity. All right. That's all I have time for, unfortunately. But you guys are working still on lab 2, right? Which is that. Coming up next week, we're going to be talking about SPI devices, which is a type of synchronous serial communication. We have a lab today, right? And that's still lab 2. So I will talk about serial communication on Monday. Okay. Yes.
You have the one on the class at the bottom.
Thank you. I made this in like 30 minutes today. I will say, yeah, the last time I taught this one, I tried drawing all of this on the board, and unsurprisingly, I did not get through all of the content in one lecture. So I learned my lesson and I updated this, but I used the wrong template, I guess. But thank you.